Hello everyone, my name is Amina Mahudawala and I am a final year electronics and computer engineering student. In this video, I'll be showcasing and explaining my project titled Cross-Domain Instance Segmentation and Style Transfer for Industrial Parts Inspection. So the main idea of this project is to address a common issue in industrial machine vision systems. Now these industries rely on machine vision for defecting for defect detection, inspecting parts and quality control. Most of these models they are trained on clean, well-controlled datasets. However, when these models are deployed, the images received by the model differ significantly. There could be lighting variations due to the environment of factories, motion blur due to moving cameras or if the parts are on a conveyor belt, sensor noise, background changes, and because of this, even well trained models may perform poorly when deployed in production. So, this is an image of steel. So, this is a steel image which has some defects that our RCNN model that our model has to detect. Now, one can see this top image is a ideal scenario, right? It is a clean image, well resolution, the defects are easily identifiable. And the model detects the faults too. However, when you have an image like the one on the bottom, which is noisy, grainy, and blurred, the model performs poorly. But collecting and labeling data under every possible real world condition, it's impractical and also expensive. Hence, this project addresses this issue by introducing domain shifting. So basically, we are first converting the messy images into clean images before giving it to the RCNN model. So for this project, we'll say the domain A are the clean and ideal images, and domain B are the messy and noisy images. So the proposed approach is we train an instance segmentation model on the clean images from domain A. Evaluate the trained model on domain B, which contains the messy images. Apply a CycleGAN based style transfer to adapt domain B images closer to domain A before giving it to the RCNN model. Re-evaluate the segmentation model on the adapted images. Compare both the visual output as well as the metrics. Now for this project, I am using the Neu-Seg Dataset. Now this dataset contains defect images of steel and the dataset has around 1700 images. It's split between training and validation data and it also contains the annotations file. So in this case, our objects would be the defects. So and the rest of the material is the background. Now the data set consists of three defect classes: scratches, inclusions, and patches. So I split the data set into two domains. Domain A is the original data set as it is, clean images, well resolution, etc. And domain B, the same images I introduced blur, noise, and lighting variations to simulate real world challenges. Now this data set it is organized in COCO instance segmentation format, which means along with the images there is a COCO annotations JSON file. So what exactly is this annotations.json file? So this particular file contains information about the dataset, so the year and exact date at which it was created, it was its URL, its descriptions. It also contains any licenses. So this is a public domain dataset. It contains the category information. So you have the incisions, patches, and scratches. And this is just a super category. You have the information about the images. So you have the image metadata, the ID, the license, the file name, the height and width. So basically the image is of 640 by 640 resolution. And most important, you have the annotations, the data about the defects. So here you can see this is the ID of the defect is 0. The image ID is also 0. This belongs to the category 3. So in this case it is a scratch. So the defect is a scratch. This defines the bounding box coordinates, the area, and this is the pixel segmentation masks. So this is what the annotations.json file basically contains, and it is used for evaluations and to calculate the evaluation metrics. Now this format is widely used and allows easy integration with uh, deep model learning with modern deep learning frameworks like Detectron 2. Detectron 2 is an open source computer vision library. It is built on PyTorch by Meta. It provides a reliable and well-tested framework for instance segmentation. So it allowed me to focus on my project rather than building the entire segmentation pipeline from scratch. It offers pre-trained mask CNN models, standardized COCO evaluation metrics, and optimized training, which makes performance comparisons consistent and reproducible. So for instance segmentation, I used a mask RCNN model. This mask RCNN extends faster RCNN. So apart from just detecting the objects, detecting the bounding boxes and class labels, it also predicts a pixel level segmentation mask for each object. So this model consists of a ResNet backbone network. This is used for feature extraction. A feature pyramid network. This handles objects at multiple scales. A region proposal network to generate the candidate object regions. ROI classification for ROI heads for classification, bounding box regression, and mask prediction. This architecture is well suited for industrial inspection tasks. So, like I said, this model was trained using Detectron 2, a research framework developed by Facebook AI. So, the entire code it's uploaded on GitHub, and I'll link it in the description. So, first, I've imported the various modules that I'll be needing. I have also registered the Neu-Seg Dataset. So, yeah, you can. So, there's the training JSONs file, the training data, the evaluation, the validation uh, annotations file, as well as the validation data. So now we can see the 1420 images they are of the training data they are loaded, and the the four classes are detected. So this is the super class, and you have the incisions, patches, and scratches, the three classes. Then we are loading an ResNet 50 feature pyramid network. So this particular model, it offers a good trade-off between performance and computational cost. So it has a good performance as well as works with consumer GPUs. Now we point to the data set that we just created. This is the training and this is the testing. Now we will set the hyperparameters. So this particular solver images per batch. This sets the number of images processed in one training step, so a batch size. This particular line defines the learning rate. It controls how the model updates the weights in each step. This is the total number of iterations. So in this case, I trained my model for 5,000 steps, and it took around 10 to 15 minutes of training. We don't need a learning rate decay because our training period is relatively short. Now, this controls how many region proposals are sampled per image for training. Now, all of these hyperparameters, I have set them based on my hardware. So here we can see the model with the COCO pre-trained weights is loaded. Since my dataset has fewer classes, the classification and mask prediction layers are automatically reinitialized. Now here we can see with, with the iterations, the total loss is going down. So at iteration 90 we were at 3.3 and at 499 we are at 1.2. Now what are these parameters? So loss CLS, it is the classification loss. So how accurately our model classified the detected objects into the correct class. This is the how well it predicted the bounding box compared to the actual boxes. Same with the segmentation, how well it predicted the segmentation masks down to the pixel level. This particular um, this particular parameter, it is a classification loss. So how well was it able to distinguish between objects and background? And RP and localization. This proposed so is the proposed region roughly in the right place? Now all of these parameters, they are added and calculated into total loss. Now after training, we will again load our latest model, the latest weights. We will load the model and we will predict. So at random from the validation set, we will pick 6 images. And these images are from the validation set. So the AI has never seen these images before. So we can see that it has picked 6 random images and performed segmentation on each of them. So after visualization, we will load the model again. And now we will evaluate the domain using the standard COCO metrics, such as the mean average precision, the mask IOU. So IOU is basically the overlap between the predicted area versus the actual defect area. So average precision at different thresholds, 50%, 75%, 95%. So when we have AP50, so it means the precision by which the model managed to cover 50 or more than 50% of actual defect area. The main metrics here are AP. So AP is actually the mean average precision over IOU thresholds from 50 to 95%. The COCO standard. AP at 50, it means the model managed to cover 50 or more than 50%. AP50 is much more lenient and easier, and AP75 is stricter and more precise. So the interpretation is the model finds the objects correctly, but the bounding box alignment can be improved. Now APS, APM and APL, these are the size-based metrics, so average precision for small objects, medium objects and large objects. So the inference here is the small objects are harder to detect, and for medium and large objects we have a strong performance, which is very common in real world data sets. Now we also have the class level average precision. So this can be used to identify strong classes. So classes which the model can detect easily and perform better on. And we can also identify weaker classes which need more data or more augmentation. This particular NaN, it appears because this class combination did not exist. It's just a superclass. So like I mentioned before, to create domain B, I intentionally applied Gaussian blur, noise injection and various contrast and brightness variations. So this was to simulate real-time camera disturbances and imperfect imaging conditions. So now when the same mask RCNN model was trained on domain B images, we can see the segmentation accuracy dropped noticeably. The mask became less precise, the confidence scores reduced. We can see even for object size and even for object size based metrics and across all the defects, there's a clear drop in precision. This clearly highlights that domain shifting is needed. Now, to address this, I introduced domain adaptation using CycleGAN. CycleGAN is an image to image translation model that learns to map images between two domains without paired training data. So it preserves the structural content while changing the visual style. That's why it's suitable for this application. So CycleGAN was trained using domain A images, which is my target, and domain B images, which is the second domain, which is the source. Now for this project, I am using the Junia's PyTorch CycleGAN and Pix2Pix library, which I have cloned. I am basically installing all the required prerequisites and dependencies. So this is the folder that has been cloned, right? So this particular folder contains um, implementations of two models. There is CycleGAN, there is the CycleGAN and Pix2Pix model. So why am I using CycleGAN? CycleGAN is used for unpaired domain adaptation, where we do not have one-to-one image correspondences, while Pix2Pix is used when paired data is available. Now, while my dataset technically has 1:1 correspondence, in real industrial scenarios, clean and noisy images are not available in pairs. They're not available in 1:1 correspondence. So now here I am giving it a destination to store translations, splitting my dataset into test and train. So we can see that domain A and B have been prepared. So here we can see the difference between a clean image and a messy image. Now in this cell we are running the train.py script. So first we are pointing to the data set with test and train. We are specifying to use the model CycleGAN. Give our parameters like batch size, load size, cropping and epochs. The epochs and most importantly the direction B to A. So it needs to know that it has to learn to convert images from domain B to domain A and not vice versa. Now after training, domain B images were translated to resemble domain A and the structural features were preserved as expected. Now again we enter our PyTorch CycleGAN and Pix2Pix folder. We are pointing to the domain B, the actual domain B that we created. Now we are pointing to the destination folder, specifying a direction B to A. And yes, we specify our load size and crop size because the default size is 256 and our images are of 640 to 640 resolution and our annotations.json file is made for this resolution. Next, here what we are doing is we are taking the translated images and creating a new folder, domain B enhanced, where we are copying it. So when CycleGAN stores the translated images, it adds a suffix. It adds this fake B suffix and at the end of each file name. So while copying, I am also removing this file name suffix and preserving the original file names to preserve the annotations compatibility. Now here we can see that the images have been saved to the domain B enhanced folder. and they also do not have the any suffixes. The adapted domain B images were then passed through the same mask RCNN model without retraining. As you can see, the results show improved mask quality, better object boundaries, and increased confidence in IOU scores. And we can see the same for the graphs as well. For every category, mean IOU, API based on sizes, classes, uh, it has increased. We can see better object boundaries, increased confidence, and increased scores. This confirms that domain adaptation does improve segmentation performance. Now, some points to note based on the observations. The model is still struggling with smaller defects even after domain adaptation. This is because smaller defects can sometimes be mistaken as part of the noise and erased by CycleGAN. Smaller defects could also be erased by the blurriness of the image. CycleGAN cannot recover lost information. Another thing you will notice is the overall metrics improvement might not seem as significant when compared to the 18% drop. But we have to keep in mind that domain adaptation helps recover part of lost performance without any additional label data. So this is demonstrating CycleGAN's effectiveness as a mitigation strategy, not complete replacement for training data. These performance observations are also not fundamental to the approach, and they are also largely influenced by the dataset size and training constraints. Using industrial scale datasets with thousands of diverse samples and access to industrial grade hardware like multi GPU systems, higher VRAM, and larger datasets and stronger compute resources, the effectiveness of domain adaptation is expected to scale significantly. So, to conclude, the models were trained on clean data and they struggled in real world environments. A domain gap adaptation using CycleGAN helped to bridge this. And the proposed segmentation pipeline helps improve the metrics without retraining the model. So, this approach can reduce data annotation costs, improve deployment reliability in industrial vision systems. I would like to reference these books that I used as well as the uh, CycleGAN library that I used that was by Junias, the the original Neu-Seg computer vision dataset, and all these references and source links I'll add them in description. And I have also uploaded all the Jupyter notebooks that I demonstrated on my GitHub. I will also link the repository in the description. I have uploaded the changed data sets which contain the artificially altered images, the CycleGAN enhanced images, and I have uploaded this on Kaggle and it is linked in the GitHub README. And I have also uploaded the latest best trained weights model on Kaggle and linked that too. The repository also contains a report of this project. Thank you for watching this video. I hope this demonstration was insightful. I would like to thank TCS ION and IIT Dhanbad for giving me this opportunity to do this project. I would like to thank my parents, family members, and friends for their constant support. Thank you.